let's learn how to use complex numbers when finding Laplace transforms. So a Laplace transform is defined as an infinite improper integral. It is going from 0 to infinity e to the minus st ft dt, and we assume that the function ft is piecewise continuous and also of exponential order, just to make sure that this integral converge. And because of this e term and the ft term, the product, so when the ft term is a trigonometric function, this integral can be difficult to evaluate. So for example, if you look at these cases, so we have t sine t, and then e to the negative 2t sine 3t, and then sine 2t cosine 3t, the product, and also maybe like both cosine, because on top of that we also get e to the minus st as an extra term. So that means if you try to use the definition and try to evaluate them, it can be really difficult to evaluate. So we can talk about like a different technique, how to use complex numbers to make the calculation easier. So everything start with what they call the Euler's identity or Euler's formula. So let's look at that and see the basics first. What they call the Euler's formula, or sometimes we call Euler's identity. So Euler's identity is, we write it as e to the it. So t is the parameter or the variable. So which is equal to cosine t plus I sine t. So t gonna change. I is the complex number. So I squared equal -1. So we know that. So I squared equals to -1. So what we're gonna do, we're gonna also write the -1. So we can write it like this. So we can write as e to the negative it. So you simply replace t by negative t. You replace t by negative t, but we know that the cosine is an even function and the sine is an odd function, and because of the even and odd property, and you can see you're gonna get this. So you can write it like this. So it's because cosine is an even function and the sine is an odd function. So because of that, so this simplifies to cosine t minus minus I sine t, because you can add the negative sign in front. So these are the two equations, and then we can actually use these two to simplify. You get a really interesting identity for sine and cosine. So let's call this equation 1 and equation 2. Now first what we're going to do, you add the two equations. So when you add the two equations, you can see that the sign get cancelled out. So you're going to get this one. So when you add the two, you get eit plus e to the minus it equal to cosine t, because sine term get cancelled out. And then when you divide by 2, you can write this one as cosine t equal e to the it plus e to the minus it over 2. So that's the cosine identity. So we can get a similar one for the sine identity as well. But when you subtract, so you subtract the two, you subtract the bottom one from the top one. So when you do that, you can see you're going to get e to the it minus e to the minus it equal 2 times I sine t. So what you do, you divide both sides by 2i. So you can divide by this term 2i. So then we can write it like this. So sine t equals e to the it minus e to the minus it over 2i. So the same, you can see same terms. One has a plus sign for the cosine and one has a minus sign for the sine one. But when you divide, you get an I term for the sine one. So that means these are the two identities. So we have cosine t is e to the it plus e to the minus it over 2. Sine t equal e to the it minus e to the minus it over 2i. Now we can do something interesting. So let's go back. So let's look at the first example. So what we're going to do, as we discussed, we're going to substitute for the sine term. We can substitute for the sine term using the identity. So we can write this one as the Laplace transform of, you can say t times, if you replace the sine t by the complex numbers, you can write this one as e to the it minus e to the minus it over 2i. So you can write it like that. And then what we can do is 2i is a constant, so you can pull it out, and also you can split them as two different, because Laplace transform is linear, so you can break it down to 2. So we can write it like this now. So we can write it, this is 1 over 2I, and then the first one you can write as the Laplace transform of you can say t e to the it. That's the first one. And the next one is you can write as minus 1 over 2I, and then it is t again e to the minus it. So after you get to this level, now we have like two ways to do it. One way is you can use the first shifting property. If you use the first shifting property, you can get these answers quickly. But let's see how we can use the definition instead, and so just to do the normal process. So let's use the definition. So what we can do, we can start with one of them. So we're going to start with the first one, and then you can see if you get the first one, only thing that you need to do to just replace I with negative y to get the other one. So let's see how it's going to turn out. So we can start with the first one. So it is a Laplace transform of t e to the it. So, and you can see if you write the definition, so let's look at the definition, which is 0 to infinity e to the minus st, and then we're going to multiply by the other term. So it is, I write e to the it first, and then t dt. Now what we can do is actually you can combine these two into one. So you can write it like this. So you can say this is 0 to infinity, and then t e to the, if you pull minus sign out, you can write this one as s minus I at t dt. So after you get to this level, now what you can do, you can either use a shortcut or the regular integration by parts technique. So let's use the shortcut to get the answer quickly. So we can use the di, so the d and I. So the derivative, we take the t term, and for the integral part, you're going to get to the e to the negative s minus I to the t term. So if you take the derivative of the first term, which is 1, if you take the integral of the second term, you see this is negative 1 over s minus I, and then e to the negative s minus it. Because the reason is, you can see this one act like a constant, so you can just divide by that. And then when you take one more derivative, it's going to be 0 on this side, and here it's going to be 1 over, because you divide by one more term, so it's going to be positive now, so s minus I squared, and then e to the minus s minus it. That's what you get. So that means now what we do, we're going to go with the plus sign for the first product and a minus sign for the second product. That means you can write the integral now. So that means what you get is this. After you write the integrals, is going to be, and we can evaluate them at infinity and 0. So what will happen when you put infinity, because of the negative term, and you can see all these terms going to go to 0. So at the limit, this will be 0. So at infinity, you get 0. Now when you plug in t equals 0, the first term get cancelled out, and then so you simply get 1 over s minus I squared. So that's what you get as the Laplace transform. That's what also this is very clear from the first shifting property. And if you use the first shifting property, you get the answer. So what is the first shifting property? Which says that if you find the Laplace transform e to the minus at ft, so what he says that you just find the Laplace transform ft and then replace s by s plus a. So opposite sign, a minus a become plus a. So that's the first shifting property, and then you can see in this problem the ft is simply 1. So ft is simply t. Ft is simply t. So because of that, the fs is 1 over s squared from the formula. You know that's from the table. So that means you just replace s by s minus I for this one, and for the next one you simply replace s by s plus I. So that's the first shifting property. So you can either get through using that also, but here what we just use the definition to get this, and because it's not a difficult integral. Now we can use the same idea to the other one, so we can finally write the answer like this. So we have this, so we can substitute for the first one and the second one. So this is the first one, and similarly for the second one, only thing that will change is just the sign of I. So it's going to be 1 over s plus I squared. So now what we do, just do the algebra, and to simplify, so what we can do is we can pull 1 over 2i out, and then take the common denominator. Once you take the common denominator, you can see you're going to get s plus I squared as a cross multiplication, and then s minus I squared, and the common denominator is the product, so you're going to get s minus I squared and then s plus I squared. And then there's an interesting simplification here. So if you multiply just one of them, so you can see if you multiply s plus I with s minus I, so you can see because of the difference of squares, it's going to be s squared minus I squared, but minus I squared is 1, so it's simply going to be s squared plus 1, because I squared is negative 1. Because I squared is negative 1, this simplifies to x squared plus 1. And then there are two of them because there's a square here, so you can see there's a square term, so that means you get the square of that. And also the top, you can see simplifies very well. All the square terms will cancel out. You get the double of the middle product, so you get a 2si term, and you get a 2si from the first one, and you get a minus 2si from the second one. And because the minus sign, they can double, so that means you finally get 1 over 2i, 1 over 2i, so you get 4si over s squared plus 1 whole thing squared. And then you can see 2i get cancelled out, so the I term get cancelled out, and also one of the 2 get cancelled out, so you finally get the answer as 2s over s squared plus 1 squared. As the answer here, we assume that s is positive. So and you can see if you try to use just the definition, this is a very difficult problem. So you need like multiple pages to get the answer, because you get like very difficult integration by parts problem here. But you can avoid all of them if you use the complex numbers, and you can see simply nicely turn out to get the answer. And also you can see you can also avoid the integration by parts here if you use the first shifting property. So you can get the second line here just by the first shifting property, as we discussed earlier. Okay, so this is how you do a problem like this. And then also, just if you haven't done this one, just try to use the definition and see how difficult the problem is. Okay, so let's try to look at another problem. Before we start the next one, you can actually get the answer for the previous one using the derivative property. And if you don't know about that one, then you can find the link in the description to learn about the derivative property. For this problem, actually derivative property would be the easiest. This is like a second best option. So let's look at the next one now. So in this problem, we have a product e to the 2t and sine 3t. So normally, like if you get a problem like that, we can use the first shifting property to get the answer because of the e term. That's like a normal way to do it. Use the first shifting property. But let's try to use the complex numbers and how we can get the answer here. So what we're going to do in this way, we're going to replace the sine term by complex numbers. So you can write this one as, so you can see we have sine 3t. So you can write this one as e to the 3it minus e to the minus 3it, and the whole thing you divide by 2i. So that's the term that you get. So that we can replace the sine term by that. So when you do that, you can see it is a 0 to infinity. So here again we just use the definition. So it is e to the minus st, and then you can see if you replace, so we have e to the minus 2t, and then we have the sine expression. So we have e to the 3it minus e minus 3it divided by 2I dt. So that's what we get. And then what we can do is again we can pull the 2I out of the integral, and then we can combine all of them. So you can see there are two terms. Since there are two terms, we can write two different integrals. So we can write this one as 0 to infinity. So we have e to the, you can combine all of them for the first term. So you get minus. From the first term you get s. From the second term you get a 2. And from the third term you get a minus 3i. So you get a minus plus t. Let's look at the first term dt. And similarly, you can get from the other term, you can say 1 over 2i, integral going from 0 to infinity, e to the minus, again, s, and then we have plus 2, and we have minus, so it can be plus now, 3i, because we already have minus sign t, dt. And that's what you get. And you can see that these integrals are not that difficult to evaluate, because you can see this term act like a constant. So because of that, we can just use the exponential property, and we know that if you integrate e to the ks dx ds, you can see that it's going to be 1 over k e to the kx plus c. So that's exactly what we're going to use here. So because of that, you can write the answer like this now. So it's a 1 over 2i. We can pull that out with a common term. So you're going to get these two terms. This is what you get for the first term. For the second term, you get a similar term like this. And both of them we can evaluate at infinity and 0. So again, what will happen when you evaluate at infinity? Because of the negative term, the e terms goes to 0. So that means when you plug in 0, the e term becomes 1. So you're going to get this. Next, what we're going to do is we're going to simplify these two and just start with the common denominator, but we can do a small trick here. So you can see we can collect the real term separately and the imaginary term separately. And when you do that, this acts like a difference of square situations. You can see this is like a minus b and a plus b situation as we discussed before. So it's going to give you a squared minus b squared term, and because of that, and also you can do the cross multiplication, so you're going to get this one as the next one. And then you can see that s plus 2 term in the numerator get cancelled out, and you double the 3i, so you get 6i, and when you divide by that, you simply get this as the answer, and this is the expected answer. So this is exactly what we get even using the first shifting property. So okay, but this is how you use the complex numbers to get like a problem like that, just directly using the definition. Okay, so let's do one more problem. So as the next one, we have sine 2t cosine 3t. So what we're going to do, we're going to replace those two terms using the complex numbers. And you know that we have these two. So sine 2t is e to the 2it minus e to the minus 2it over 2i, and cosine is this. Now what we do, we're going to substitute these two into the expression. So it is the Laplace transform of, so let's substitute that. So next what we do, so we substitute for the two, for the sine and cosine. Next what we do, we can actually pull out the 4i term, because that's a constant, and also we can distribute the top, just multiply through, and then we're going to get this. So after we get to this level, now what we can do, we can use the first shifting property. So it says that the Laplace transform of e to the minus at ft equal f s plus a, but in this example you can see the ft is just 1. So if it is 1, and then you can see the fs is 1 over s from the table. So that means you can write the answers now for each one. So you're going to get 1 over 4i as a factor. We can write outside, and then we can write separate terms. So the first one going to be 1 over, just replace s by s minus 5i in this case. So s minus 5i, and the next term going to be 1 over s plus I, and the next one is 1 over s minus I, and then minus 1 over s plus 5i. That's what you get. This just directly from the shifting property. Now what we do, we're going to combine the first and the last. When you combine those two, and then you can see, you can use a cross multiplication, so you get this one. So from the first and the last, so you're going to get the 10i, the numerator going to be 10i, the bottom going to be, because of the difference of squares and the complex number I squared is 1, so you can negative 1, so you can see you're going to get a squared plus 25. That's what you get from the first one. And then you're going to combine the middle two, same thing happen. So you can see you're going to get plus, you're going to get 2i over s squared plus 1. That's what you get. And then what we do, we can divide by 4i outside. So the I term get cancelled out now. And then this simplify really well. So you get 5 over 2 s squared plus 25 from the first term. And from the second term, you can see, so just 1/2. So 1 over 2, so it is s squared plus 1 as the answer. So this is the answer you're going to get as a final one. And you can see this simplifies really well. And this is the quickest way to get the answer. Because if you try to use the definition, this is going to be a really long problem. And you can also use other techniques for this particular problem. So this is like kind of one way to get the answer quickly. Okay, now you can try these problems as practice problems and see whether you can write the answer in the description as a comment. Okay, so thank you so much for watching. So use complex numbers method that we just discussed, complex numbers method, to find the Laplace transform of the following functions. So try to find the Laplace transform of these 5 functions now. And then you can put the answer as a comment in the description.